And I do, coming to you from the Minecraft world. Right, so today we're going to be having a look at waves and a more fun way of looking at waves in the form of a couple of simulations. So in your team, there's a document that has some instructions on a couple of simulations I'd like you to try out, which I'm going to do a short demonstration about how you'd be going about doing that. All right, so this is roughly what the guide looks like. There are 5 simulations in total, which, not to overwhelm you, there is only one simulation that I'd like you to try and to attempt this activity and just write a short bit about that. But these 5 simulations do show a lot of the more interesting properties of waves besides the normal calculations that we do. Right, so the first simulation is waves in a string, something you might have seen before, but I'd like you all to try this yourself and to see if you can demonstrate the properties of waves that we've been looking at. So very quickly, if I can demonstrate a manual wave or a manual pulse, which looks very bad. This button over here for pulse will allow you to send out a perfect crest going towards a fixed end and bouncing back. Now, to get ideal results, you're going to want to turn down the damping to 0 so that when I now send the pulse, it doesn't get smaller over time. So you're going to investigate how does a pulse reflect at a fixed end, at a loose end, and if you let it go out the window, it completely disappears. Then you're going to be testing this out with waves, a series of pulses, and in particular to try and create a pattern of standing waves. So standing waves are a tricky thing, but it occurs when you have waves that have exactly the right frequency that causes them to interfere with each other. Because what's happening here is as I'm sending out a crest, it bounces back off the fixed end and comes back interfering with the next crest that I'm sending through. And in that way, it creates a series of, shall we say, chaos, it seems. But if you look at any specific point, you'll see how the amplitude of the wave gets bigger and then it gets smaller and then back to 0. So if you adjust the frequency to exactly the right numbers, and there is a method for these calculations, for instance, a frequency of 0.4 Hertz, the crest that I send interferes with the crest coming back at exactly, you get one huge crest that gets bigger and bigger. If I change the frequency to any multiple of that 0.41, something like 1.62, see a very interesting pattern coming about here if you can see through the chaos. And if I pause it at just one instance, you can see it goes off the screen. Just going to reduce the amplitude so the waves are not so gigantic. And if I pause for a second here, you can see that there are 2 crests and 2 troughs. That makes 2 complete waves. As I resume, these waves constructively interfere with each other at this point, and that creates an even bigger crest. But if I move my cursor to this green circle here, you can see that it barely moment, you can see that there are 2 crests and 2 troughs. That's 2 complete waves. And as I resume this, you can see that at this point, the amplitude gets bigger and bigger as a result of constructive interference. And those points we call antinodes. These points over here, like this green circle in the center, barely seems to move at all. And that's as a result of destructive interference, which we call nodes. Right, looking at the next simulation on wave interference, the one that you need to do and write some observations on. So the first simulation or tab on waves demonstrates how if we have a drop in water, this is what we would see from the top. Now this button on the left here is to choose whether you want to just have a single drop at a time, which we call a pulse, or a wave, which I'm going to be looking at. This button here on the side lets us see what the wave looks like from the side view. And here we can see the crests and troughs. One thing you will notice, and especially if I put this graph box on, is you can see that the amplitude of the wave decreases over time. And that is what happens in reality because of damping that tends to reduce the amplitude of a wave. Instead, I'm going to use this sensor over here, just drag it out of the corner, and I move one sensor onto any point in the wave. And here you can see the nice familiar waveform where the amplitude doesn't change at that point, meaning each crest is exactly the same. On every graph, the first thing you want to see is what the axes are showing. This is showing water level, that's showing the amplitude versus time. Other things I can change in the simulation is I can change the frequency of the wave. So if I have a maximum frequency, the waves occur more often. And so we see the period on this graph here is much shorter. You can also change the amplitude. That would of course just change the height of the wave. As you can see, a high amplitude, high water level. Low amplitude, we have a very low water level. Okay, of the simulation, the one that you need to do the activity on is the second tab for interference, because you want to see how do two waves interact with each other. So I'm going to turn on both tabs, creating two droplets, and observe what happens. So the aim of this is for you to play around with the buttons. There's no specific pattern that you need to obtain. If you obtain something different and interesting, well, that's something to be explained. So here's something you might not have seen in everyday life, but we see a very interesting pattern that at centers in the middle, the wave continues as normal, but there are specific lines where the water doesn't seem to be disturbed at all. And that's very similar to what we saw with waves in a string, where we had points, we call them nodes, where destructive interference happens and the wave doesn't move at all. So if I pick up one of these sensors here, just to see what is happening. So if I put it near this spot here, just going to decrease the amplitude. Don't need such gigantic waves. We can see the amplitude by this gray cursor is alternating. If I put it where there were one of those dark lines, that's the very faint gray line. You can see the amplitude is a lot smaller there. That's as a result of the two waves, the crest of one and the trough of the other, meeting and cancelling each other out just across these lines. Other things you can control is you control the frequency of these waves, like we did in the first simulation. That wouldn't affect the interference pattern. And just so you can see this very clearly, I'm using a maximum amplitude and a maximum frequency. Here you can see there are almost triangular patterns where the two waves reinforce each other and make even bigger crests along the central region. But along these lines on the side, we have those nodes where the wave cancels out and the water viewed from the side would appear very calm. Could also try this with two sound waves. Make sure your sound is up for this. So this could happen if we have two sound waves happening at the same time. We get a similar pattern that we could see, but of course we couldn't hear or we couldn't see the sound. If I had to be standing at this white cursor, because we have destructive interference, a person standing here would not hear any sound. If you have sound waves at exactly the right frequency, matching up at exactly the right time, they will cancel each other out and you won't hear anything. Whereas on this other gray circle, near the center beam, center region, you would hear a much louder amplified sound due to constructive interference, and that we called antinodes. Right, so that's the investigation I want you to do on interference. There are a couple of questions that you need to answer, a few things to try, and you must answer this on page 9 of booklet 1. There are some lines there for a ripple tank, and to just describe your observations in your own words, point form please, and then to also try to explain why some of these things are happening, which I've just summed up in the last 5 minutes. Right, and then lastly, I'd also want you to draw a sketch or two of what you see, or if it might be easier, to just insert screenshots, photos into your notebook. But once we have these laptops, that will be a lot faster and easier for you to do. Okay, just going to play around. That's really the whole point of these simulations, is to play around. What happens when we have some slits? So now I'm sending a single water wave through a narrow opening. And as predicted, it will obviously go through that point and not through the wall. But what you also notice is that the wave seems to be spreading out as it goes around a corner. And that's something that we call diffraction, the property of a wave to bend around a narrow slit or a corner. If I had to make the slit slightly narrower, or a lot narrower, we can see that bending is a lot more pronounced. And that's something explained by Huygens principle, which says that every point on a wave front, the front of a wave, acts as a source of secondary wavelets. So that means every point on this wave approaching, when it reaches the slit, starts a new wavelet, a smaller wave, that spreads out in all directions. So that spreading out is what we called diffraction. The diffraction experiment itself, on the last tab, uses light. So here I'm going to shine a red beam through a narrow slit. This is what you would observe if you had to do this in real life. And what you see on the right-hand side is the pattern that comes out on the screen, which looks like some circular rings. We call them fringes. What I do want you to pay attention to is how you have a bright spot right in the center, a dark line, another bright line, dark line, and so on, that fade away as you go further away. And to explain why we have these bright and dark lines, the bright lines are caused by constructive interference. The wavelets reinforce each other and become brighter. And the dark lines is caused by destructive interference, where they cancel each other out. Okay, the next simulation on Waves intro is the one I just looked at. The next simulation, so this is simulation 4 on Fourier, is a very advanced way of looking at waves, but I just want you to try this wave game. Fourier analysis is basically about how any waveform can be made up of a combination of other waves. So this game is about trying to create a wave that will match up with the one at the bottom. So these two sliders here you can use to adjust the amplitudes of the two waves, and what you're trying to do is to get them to match up to the purple wave. So I'm controlling the blue and the green wave. You can see the individual waves under harmonics. A harmonic is basically a wave that has one frequency. So it's those nice, neat waves. And at the bottom, you can see the sum of those two waves when we add them together or when they interfere. And I'm trying to get my two waves to match up to the purple one. The black line is representing the sum of my two waves. So if you just look at what happens when I take the green and the blue waves, notice how the red wave is actually a combination of two separate waves. It doesn't have a very neat period and frequency that we can measure, but that's because it's a combination of those two waves. So if I look at this, the purple wave seems to be made of actually just one wave. I'm going to check, and not correct. If I show the answer, it was actually adjusting the amplitude of the blue wave. The difference between the blue and the green wave, and you see what it is? It is the period of the wave. Wavelength, sorry. This is a distance graph, x. Anyway, Fourier analysis is a bit advanced, but this is a game to try about how waves combine with each other. And finally, the last simulation on bending light is similar to the practical, but this is a simulation. A simulation is a program designed with the laws of physics that gives us perfect results, not something you'd see in everyday life. In that way, it can't really be regarded as real science, just like the matrix can't be regarded as the real world. Okay, so if I switch on this laser beam, we can see it's moving from air to light. And what this shows is how light is reflecting, bouncing off the surface, staying in the same medium of air at a specific angle. And if I pick up my protractor here, remember a protractor to measure angles is always placed with 0 at the normal, because I'm trying to measure the angle of incidence, which is the angle from the normal to the incident ray, the ray coming in. So if I use my protractor, I'm getting an angle of about 57, 58 degrees on this side. If I measure on the other side, the angle of reflection towards the reflected ray, I get the same angle, an angle of about 57 degrees. And that is the law of reflection. To adjust the angle of the laser, just drag it sideways with these green arrows, and you can see that the reflected ray is completely symmetrical to the incident ray. Now, if I look at the line of light coming into the water, that is called refraction. If I had to follow this light beam in a straight line, we can see it seems to be bending slightly towards the normal. I can check that by measuring the angles. So my angle of incidence, I'm going to set it to be 30 degrees exactly. Then to measure the angle of refraction, looking at the bottom of the protractor, from 0 to that angle is about 22 degrees, which is less than my incident angle. So when a light beam goes from a less dense medium like air into a more dense medium like water, it bends towards the normal, so the angle of refraction is smaller than the angle of incidence. Now, even though I use the word density here, it's not the same density as mass over volume. It's something called the optical density, which is measured by the index of refraction. Now, you don't need to know these numbers. It actually just puts a number to different materials based on their ability to bend light. So if I had to choose, say, water to water, light will of course just go in a straight line because there is no refraction. I'm going to keep this angle fixed at 60 degrees. If I change my second medium to air, I'll come to that in a minute. If I change my second medium from water to glass, because water has a refractive index of 1.33 and glass slightly more than that, the angle of light is bending slightly towards the normal. So here was air and glass. So I'm keeping my incident ray fixed. Notice where the refracted ray is. Air to water, it doesn't bend as much. Now, if I had to make it from water to water, that was a straight line. Water to glass, it bends slightly away. Okay, I'm going to go the other way, from water to air. Let's put ourselves in the position of the fish. So the fish being in the water over there, upside down. So here we can see the reflection of light happening inside the water. That will always happen. And we can see the refracted ray is now bending away from the normal because it's going from a more dense medium to a less dense medium. Now, if I adjust the angle of incidence, started at 0, there it's just going in a straight line. As I increase the angle, the reflection will always be the same angle. The refraction will always have a bigger angle. But as I keep turning it, notice how the refracted ray is getting closer and closer to the water. And at some angle, it will line up perfectly along the surface of the water. And that angle is something we discovered is called the critical angle. It's the angle of incidence where the angle of refraction is 90 degrees. Because at the moment, my refracted ray is sitting exactly on the water. From the normal to the water is 90 degrees. So my angle of refraction here is 90 degrees. At any incident angle more than that, light is going to completely reflect inside the medium. Notice there's no more refraction happening. And this is what was called total internal reflection. So if you were the fish sitting in water, you would not be able to see anything outside in the air from this angle because any light would be completely reflected back inside the water. Something to try the next time you're in a swimming pool. All right, the next tab is about prisms. So you also investigated this with a prism. So I'm just picking up a glass prism. You can choose the material in the corner here. And you can see how the light ray bends around. Now with this prism, I'm going to start with the rectangular one. There are two refractions happening here because firstly, we're having a refraction at this point from air into glass and a second refraction from glass into air. So there's actually a double refraction happening here. So this is more just an investigation to play around with, see how things happen. I showed you total internal reflection with just the surface of the water. In this prism here, you've got to adjust the angle. So to move this thing, you just drag the laser around. And to adjust the angle, you do this. So this is what most of you discovered when you shone the light ray at the prism. If I bring it from, actually, if I put it here, the angle of refraction, or the angle of, looking for my normal line, the angle of refraction is between the normal line and the refracted ray here. This is the interface I'm looking at between glass to air. So if I want to decrease that angle, I'm going to have to put my laser on this side. Now you can see it more clearly. So if I go from a very high angle, like this, you can see that it refracts out of the glass. As I tilt this slightly, you can see how my angle of incidence, that's between this normal at the bottom and the incident ray in the glass, is getting bigger and bigger. And at some point, it causes the light to refract directly on the surface, the critical angle, almost about here. And at any angle larger than that, it will now reflect inside the prism. Okay, so you can experiment with some different shapes. Quickly going to show you those who wear glasses, how glasses work. So we are not studying lenses, but lenses are used to correct vision when the surface of your eyeball, the cornea, and the lens inside it do not have the correct bending power. So for instance, if this is your eyeball, of course it's not your entire eye that focuses light, but we're not going to study the eye unless you're going to become an optometrist. Too many prisms on the page. When light goes through a circle, you can see how each ray of light gets bent and they meet up at a certain point. And that point is where the image focuses clearly. So if your eyeball or the cornea of your eye, the lens, doesn't have the right curvature, optometrists give you glasses or contact lenses which are curved in such a way that they adjust how light enters your eye. So by using a correct combination of lenses, like these two lenses here, they focus the light in such a way that it can correctly form on the back of your eye. But anyway, optometry is a lesson for another time. Just play around with these things and see what interesting things you can discover. For instance, in a sphere, how many angles of reflection can you get? How many times can you get light to reflect inside the prism? Right, so then the last tab with more tools just has two new tools about the intensity and speed. So if I take this light beam, I can also measure the speed of light. So in air, the speed of light is 1c, where c is the speed of light. In water, the speed of light decreases. Now to visualize this as a wave, the first thing you can notice, or one of the many things you notice, is that as the wave moves into the water, the little pieces of the wave, these are transverse waves, the crests are closer together, which indicates we have a shorter wavelength. So this is the relationship in the wave equation, V equals F lambda. As the wave enters the water, the speed decreases, and therefore the wavelength decreases as well. You can visualize V equals F lambda. V is directly proportional to the wavelength. This intensity meter in green can also show us what percentage of the light gets refracted, 90.69%, and what percentage gets reflected, about 9.31%, which is so small that we very often don't see a lot of the reflection of light. If I were to change the angle, you can see how that does affect the percentage that gets reflected and refracted. That's an interesting phenomenon to study in another time. And then the other tool is time. So this time meter, if I put one sensor on the wave, shows us how the amplitude of the wave changes with time. If I move the same sensor into the water, you can see how the amplitude is only slightly less. So if I put two sensors at once, the dark gray one is in air, the light gray one is in water, you can see that the light gray one has a slightly smaller amplitude because some of that light rays was reflected. Okay, so those are the 5 simulations. This last thing I'm looking at is a virtual oscilloscope, which is basically a sensor that represents sound waves as transverse waveforms. So as I'm speaking now, it's using my microphone to measure the frequencies and plot them on this scope. So this is again something I just want you to play around with to see how different sounds create different waveforms. So try to whistle. And if you press the freeze live input, you can see a nice clear waveform. And that's because whistling is one single frequency. When I talk, on the other hand, it's a complex combination of different frequencies that gives us this interesting waveform. The other link has a similar function of an oscilloscope, but it also has something called a spectrum analyzer, a sound analyzer, which takes a combination of sounds and represents it as where are the different frequencies of that sound coming from. So if I speak, and just pause this for a second, you can see that in that last word, that sound I was producing was made of a combination of these frequencies. So again, investigate with different sounds. Whistling, you can see, has a very sharp frequency, but speaking or humming will have a whole combination of different waveforms. All right, so before I end, just want to share with you an amazing video by Cymatics called The Science of Music.
The film you're about to see has no characters. If you spare a little of your imagination, it is a film to describe to you the effect of cymatic frequencies on matter. Everything owes its existence solely and completely to sound.
Right, so that's all from me. Have a great one, everyone, and make sure that you do try those few observations on that one simulation. Goodbye.